Electromagnetic interference, also known as EMI, can be a significant factor when an oxygen machine affects a satellite receiver. Oxygen machines possess electrical components such as motors, compressors, and transformers. These components can generate electromagnetic radiation capable of interfering with the operation of electronic devices. The satellite receiver's signal can be disrupted by the strong EMI emitted by the oxygen machine. Grounding is essential to maintain a proper electrical current flow. If either the oxygen machine or the satellite system lacks proper grounding, EMI can propagate through the electrical system and cause interference. Defective or damaged cables or components within either the oxygen machine or the satellite system can lead to EMI generation or connection problems. These issues can manifest as signal freezing. Resonance may also play a role. If the operating frequency of the oxygen machine aligns with the resonant frequency of the satellite receiver's circuitry, the receiver might amplify the interference and cause freezing on specific transponders. To address these issues, firstly, examine all cables and connections within both the oxygen machine and the satellite system, ensuring they are secure. Secondly, experiment with different power outlets. Plug the oxygen machine into an alternate outlet on a separate circuit to rule out potential wiring problems. Thirdly, employ a power conditioner or surge protector. A power conditioner or surge protector can filter out EMI and shield electronic devices from voltage fluctuations. Fourthly, install a ferrite choke. A ferrite choke is a passive component that can be installed on the oxygen machine's power cord to mitigate EMI emissions. If these steps prove ineffective, it's advisable to contact the manufacturers of both the oxygen machine and the satellite system for expert assistance and possible solutions. It is important to ensure that all connections are not loose. Electromagnetic interference, often abbreviated as EMI, is a disturbance generated by an external source that affects an electrical circuit by electromagnetic induction, electrostatic coupling, or conduction. EMI can interrupt, obstruct, or otherwise degrade or limit the effective performance of the circuit. EMI can be generated by a variety of sources, both natural and man-made. Natural sources include lightning, solar flares, and the Earth's magnetic field. Man-made sources include electrical motors, radio transmitters, microwave ovens, and computers. Proper grounding is a critical aspect of electrical safety and electromagnetic compatibility. It provides a low-impedance path for fault currents to return to the source, helping to protect equipment and personnel from electrical shock. It also helps to reduce electromagnetic interference by providing a common reference point for electrical signals. Grounding works by creating a conductive path between electrical equipment and the earth. This path allows fault currents to flow safely to the ground, where they can be dissipated without causing harm. To ensure effective grounding, several key principles must be followed. Firstly, a low impedance path to ground is essential. This minimizes the voltage rise during a fault and ensures rapid clearing of the fault current. Secondly, the grounding system must be designed to handle the maximum fault current that could occur. Thirdly, all metallic parts of electrical equipment must be bonded together and connected to the grounding system. Fourthly, the grounding system must be regularly inspected and tested to ensure its effectiveness. Damaged or defective cables or components can be a significant source of electrical and electronic issues. Cables can become damaged due to physical stress, age, environmental factors, or improper handling. This damage can lead to a variety of problems, including short circuits, open circuits, and reduced insulation resistance. Components can fail due to manufacturing defects, overheating, overvoltage, or general wear and tear. These failures can cause a range of malfunctions, from minor performance issues to complete system failure. To identify damaged cables or components, visual inspection is often the first step. Look for signs of physical damage such as cuts, abrasions, or melted insulation on cables. Inspect components for burn marks, cracks, or bulging. Electrical testing can help to confirm the presence of faults. Continuity tests can identify open circuits, while insulation resistance tests can detect insulation breakdown. Voltage and current measurements can help to pinpoint malfunctioning components. If damage is found, the affected cables or components should be replaced immediately. Repairing damaged cables is generally not recommended, as it can be difficult to ensure a reliable and safe repair. When replacing components, use parts that are equivalent or superior in quality to the original components. Resonance is a phenomenon that occurs when a system is subjected to an external force or frequency that matches its natural frequency. At resonance, the system's amplitude of oscillation reaches a maximum, which can lead to significant amplification of energy. In electrical circuits, resonance occurs when the inductive reactance and capacitive reactance are equal. This condition can lead to a large current flow, even with a small applied voltage. Resonant circuits are used in a variety of applications, including radio transmitters, receivers, and filters. However, resonance can also be undesirable, as it can lead to excessive voltage or current levels that can damage components. To avoid unwanted resonance, it is important to carefully design and analyze electrical circuits. This may involve adding damping components, such as resistors, to reduce the amplitude of oscillation. It may also involve adjusting the values of inductors and capacitors to shift the resonant frequency away from any potential sources of excitation. Power conditioners and surge protectors are devices designed to protect electrical equipment from voltage fluctuations and power surges. Power conditioners provide a stable and clean power supply by regulating voltage, filtering noise, and suppressing transients. They are used to protect sensitive electronic equipment, such as computers, audio equipment, and medical devices. Surge protectors are designed to protect equipment from sudden and brief voltage spikes, known as surges. Surges can be caused by lightning strikes, power outages, or the switching of electrical equipment. Surge protectors work by diverting the excess voltage to ground, preventing it from reaching the protected equipment. Power conditioners and surge protectors are essential for protecting valuable electronic equipment from damage caused by power fluctuations. They can help to extend the lifespan of equipment and prevent data loss or corruption. Ferrite chokes are passive electronic components used to suppress high-frequency noise in electrical circuits. They are typically installed on cables or wires to reduce electromagnetic interference. Ferrite chokes work by increasing the impedance of the circuit at high frequencies, thereby attenuating the noise signal. They are made of a ferrite material, which is a ceramic compound with high magnetic permeability. Ferrite chokes are widely used in electronic devices, such as computers, audio equipment, and power supplies, to reduce electromagnetic interference and improve signal quality. They are available in a variety of shapes and sizes to suit different applications. When selecting a ferrite choke, it is important to consider the frequency range of the noise to be suppressed, the impedance required, and the current rating of the choke. It is also important to ensure that the choke is properly installed to ensure optimal performance. To ensure proper grounding of electrical systems, several key steps should be followed. Firstly, all metallic enclosures and equipment should be connected to the grounding system. This can be achieved by using grounding conductors, such as copper wires or straps. Secondly, the grounding system should be connected to a grounding electrode, such as a ground rod or a metal water pipe. The grounding electrode should be buried deep enough in the ground to ensure good electrical contact. Thirdly, the grounding system should be regularly inspected and tested to ensure its effectiveness. Grounding conductors should be checked for corrosion and damage, and the resistance of the grounding system should be measured to ensure that it is within acceptable limits. In addition to these basic steps, there are a number of other factors that should be considered when designing and installing a grounding system. These factors include the type of soil, the presence of underground utilities, and the potential for lightning strikes. By following these steps and considering these factors, it is possible to ensure that electrical systems are properly grounded and that personnel and equipment are protected from electrical hazards. Testing different power outlets can help to identify and isolate electrical problems. If a device is not working properly, plugging it into a different outlet can determine whether the problem is with the device itself or with the outlet. If the device works in a different outlet, the original outlet may be faulty or overloaded. Using a power conditioner or surge protector can help to protect electronic devices from voltage fluctuations and power surges. Power conditioners regulate the voltage and filter out noise, while surge protectors divert excess voltage to ground. Installing a ferrite choke on the power cord of an oxygen machine can help to reduce electromagnetic interference. Ferrite chokes are passive components that increase the impedance of the circuit at high frequencies, thereby attenuating the noise signal. When troubleshooting electrical issues, it is important to follow proper safety precautions. Always disconnect power before working on electrical circuits, and use appropriate personal protective equipment, such as gloves and eye protection. If you are not comfortable working on electrical systems, it is best to consult a qualified electrician. Electromagnetic compatibility, or EMC, is the ability of electronic equipment and systems to function satisfactorily in their electromagnetic environment without introducing intolerable electromagnetic disturbances to other equipment or systems in that environment. EMC involves two main aspects. Firstly, electromagnetic interference, or EMI, which is the generation of unwanted electromagnetic energy that can disrupt the operation of other equipment, and secondly, electromagnetic susceptibility, or EMS, which is the sensitivity of equipment to electromagnetic interference. To achieve EMC, it is important to minimize the EMI emissions from electronic devices and to design equipment to be less susceptible to EMI. This can be achieved through a variety of techniques, including shielding, filtering, grounding, and proper circuit design. EMC is a critical consideration in the design and operation of electronic equipment and systems, particularly in environments where there are many potential sources of EMI. Failure to address EMC can lead to a variety of problems, including equipment malfunction, data loss, and safety hazards. Electrical noise is unwanted electrical signals that can interfere with the operation of electronic circuits. Noise can be generated by a variety of sources, including electromagnetic interference, thermal noise, and shot noise. Electromagnetic interference, as previously discussed, is a disturbance generated by external sources that affect circuits through electromagnetic induction, electrostatic coupling, or conduction. Thermal noise is generated by the random motion of electrons in a conductor. Shot noise is generated by the discrete nature of electrical current. Electrical noise can degrade the performance of electronic circuits by reducing signal-to-noise ratio, causing errors, and even damaging components. To reduce the effects of noise, a variety of techniques can be used, including shielding, filtering, grounding, and proper circuit design. Shielding involves enclosing electronic circuits in a conductive enclosure to prevent electromagnetic interference from entering or leaving the enclosure. Filtering involves using electronic filters to attenuate unwanted noise signals. Grounding involves providing a low impedance path for noise currents to flow to ground. Proper circuit design involves minimizing the generation and propagation of noise within the circuit. Voltage fluctuations are variations in the voltage of an electrical power supply. These fluctuations can be caused by a variety of factors, including changes in the load on the power supply, variations in the voltage of the incoming power line, and the operation of other electrical equipment. Voltage fluctuations can have a number of negative effects on electronic equipment, including reduced performance, data loss, and component damage. To protect equipment from voltage fluctuations, a power conditioner can be used. Power conditioners regulate the voltage and filter out noise, providing a stable and clean power supply. Power surges are sudden and brief increases in voltage that can damage electronic equipment. Surges can be caused by lightning strikes, power outages, or the switching of electrical equipment. To protect equipment from power surges, a surge protector can be used. Surge protectors divert the excess voltage to ground, preventing it from reaching the protected equipment. Surge protectors typically use metal oxide varistors, or MOVs, to divert the surge current. MOV are semiconductor devices that have a higher resistance at normal voltages but a lower resistance at high voltages. When a surge occurs, the MOV resistance drops, diverting the surge current to ground. Surge protectors are rated by their surge current capacity, which is the maximum amount of current that they can safely divert. It is important to select a surge protector with a surge current capacity that is appropriate for the environment in which it will be used. Loose connections can cause a variety of electrical problems, including intermittent operation, reduced performance, and overheating. Loose connections can also create a fire hazard. To prevent loose connections, it is important to ensure that all electrical connections are properly tightened and secured. When making electrical connections, use the appropriate tools and techniques. For example, when tightening screws, use a torque wrench to ensure that the screws are tightened to the correct torque. Also, make sure that the wires are properly stripped and inserted into the connectors. Regularly inspect electrical connections for looseness or corrosion. If any loose connections are found, tighten them immediately. If any corroded connections are found, clean them with a wire brush and apply a corrosion inhibitor.